Recall that a discrete random variable is captured entirely by its probability mass function. In practice, though, you rarely start from scratch. A small number of distributions show up frequently, and almost all of them come from counting. In this video, we tour 5 of them: the Bernoulli, the binomial, the Poisson, the geometric, and the uniform, each with its own counting story and its own bar chart. And in the middle, we'll see something surprising. The binomial, in a certain limit, turns into the Poisson. Start with the simplest random variable there is. A Bernoulli random variable takes only 2 values, 0 and 1. It equals 1 with probability p and 0 with probability 1 minus p. That's the entire distribution. As a bar chart, it is just 2 bars, possibly a tall one and a short one, and here p is 1/4. Every Bernoulli is really a coin flip, a biased coin that comes up heads, which we call 1, with probability p. It looks trivial, but it is the atom from which the next 2 distributions are built. Now flip that coin n times independently and count the ones. The number of successes in n independent identical Bernoulli trials is a binomial random variable. Its PMF is n choose k times p to the times 1 minus p to the n minus k. The n choose k counts which trials succeeded, and the powers give the probability of any one such pattern. Sum over all k, and the binomial theorem gives exactly 1. With n equal to 8 and p a quarter, the bars rise to a peak near 2 and taper off. Here's the story. A soda promotion pays $1 under 1 cap in 4. Buy 8 bottles, and the number of winners is binomial with n8, p 1/4. The chance of winning more than $4 is the sum of the PMF from 5 up to 8. The next one counts occurrences over time. A Poisson random variable has PMF lambda to the k over k factorial times e to the minus lambda for k equals 0, 1, 2, and up. It normalizes beautifully. The sum of lambda to the k over k factorial is just the Taylor series for e to the lambda, which cancels the e to the minus lambda to leave 1. With lambda equal to 2, the mass peaks at 1 and 2 and decays. Poisson is the go-to model for counts: requests hitting a server, arrivals in a queue, calls in a minute. If requests arrive at rate lambda per second, the probability that none arrives in a given second is simply e to the minus lambda. Here's the payoff, and it connects the last 2. Fix a rate lambda and let each of n trials succeed with probability lambda over n, so as n grows, each success gets rarer, but the expected count stays lambda. With 15 trials, the shape is close, but still a little rough. 25 trials and it sharpens. 35 trials and the bars settle right onto the Poisson curve drawn faintly behind them. In the limit, the binomial becomes the Poisson. This is why a Poisson with lambda equal to n times p is such a good approximation to a binomial when n is large and p is small. Instead of counting successes in a fixed number of trials, now wait for the first success. Keep running Bernoulli trials until you get a 1. The number of trials that took is a geometric random variable. Its PMF is 1 minus p to the k minus 1 times p, the probability of k minus 1 failures followed by a success. Because each extra trial multiplies by 1 minus p, the bars decay by a constant factor, a steadily shrinking staircase. And the geometric hides a remarkable property. It is memoryless. Given that you've already waited more than k trials, the probability you need j more is exactly the original probability of j. The process forgets its past completely, and the geometric is the only discrete random variable that does. The last one is the picture of pure symmetry. A discrete uniform random variable takes n values, all equally likely, each with probability 1 over n. Its bar chart is perfectly flat. Here n is 8, so every bar sits at 1/8. We've quietly met this one already. A fair die and a fair coin are both discrete uniforms. So there is our gallery: Bernoulli, binomial, Poisson, geometric, uniform, 5 distributions, each tied to a counting story, and the binomial folding into the Poisson in the limit. Next, we'll take a random variable and transform it and follow what happens to its PMF.